Good morning, everybody. I've really gone back and forth as to exactly what to include in this video. At one point I thought I would just do every single thing that happened step by step, but it was just becoming this video that was so long and monotonous that, I don't even know if my mom, my #1 fan, would make it through it. So I've decided to just kind of include what I would call some of the more nuanced topics I thought were interesting, some of the outliers, some of the weird things that happened. I mean, there was exceptions, wood being a natural material. It didn't all fail exactly the same. So I've basically decided to include some of those interesting points, as well as that second experiment I left out. But you really need to now go and watch that summary video. It's going to cover the major themes, an overview of the materials, an overview of the joints. And yeah, if you don't watch that video first, then you're going to lack the context for this one to make much sense at all. So please go watch that and then come back here if you're still curious to learn some of the in and outs and some of the things that made me kind of scratch my head. And yeah, I think hopefully you guys find this one interesting as well. But yeah, you got to watch that other video first. So let's just get right into it. The first experiment, beam strength test. The footage from this is insanely boring. I'm literally just hanging a couple weights over and over from different beams. But if you watch the summary video, the thing that surprised me the most about all of this was that maple and pine had the same amount of deflection. So right after I saw those results, I was scratching my head. I was like, is this real? Am I just having some weird wood samples here? So I went to a resource I use quite a bit called the Wood Database. If you're a woodworker, you're probably familiar with it, but it just is a great online resource that lists basically every technical spec and every characteristic of almost any wood species you could get. And sure enough, when you look up, I think the maple species and the pine species that I can source here locally, their elastic modulus is basically identical. So to me, those are always neat little moments or neat little anecdotes when you kind of it kind of feels like, the textbook is coming to life. These numbers you've read on a page in practice, does the world actually work like this, in an application? And sure enough, that was really cool to see. They deflected basically identically, and that's what the textbook definition tells me as well. And just to ramble for one more minute about the Wood Database, there's this really geeky woodworking podcast called Shannon's Lumber Industry Update. If you like woodworking or have a curiosity about it, it is a great place to just fill your mind with random facts about different woods. But Shannon often conveys that the way he uses the Wood Database is if you're really familiar with working with a certain species and suddenly you want some different wood species, or maybe you come across a different species to work with and you're wondering, how is this going to work? What's its rot resistance? What's its hardness, etc.? Then he uses it as a comparative. So if you're really familiar working with maple or something like I am, and let's say you come across some random species you've never worked with, you can go to that, and instead of getting fixated on oh, the Janka hardness is exactly this, you can just look as kind of a comparison and be like, oh, this is a little harder, so I should expect that. You can read the comments about what its workability is and such. So yeah, Wood Database, great resource for basically learning about wood and kind of planning future projects and looking for certain attributes in a species, to fit your design, I guess I would say. All right, I think that's all I've got to say about that experiment. So onwards to the omitted test from the summary video, and that has to do with joint flex. And for this test, I'll just play the intro I had recorded before I actually did that test. So got a handful of joints glued up here. They've been drying about 3 days, and our second experiment is going to concern kind of the concept of joint flex, which I personally think is really important when designing and building furniture for a van. Every day you're living or using your van, everything in it flexes, I think, whether you think so or not. If you go over a pothole, everything on your shelves bounces up and down. That cabinet had to absorb all that force. You're jumping around in bed, that bed frame has to flex. And maybe most of all, the bodies of the van that we've bolted all our cabinets to, hopefully fairly securely, is flexing all the time you're driving, anytime you're especially when you're off-roading. And to kind of demonstrate that, let me take you guys outside here and show a couple things about this van here. So as you see, this front tire, got it up on a ramp. And if we walk around the van to the opposing tire, the rear passenger side one, it is also up on a ramp. So as you see, the entire van, basically kitty corner, the body's kind of torqued. You can see this other tire. I even had to spin it a little to get up on these blocks here. Yeah, it's pretty flexed out. Not too bad. Still got all 4 tires touching the ground. But if you come over and look at this back door, these body lines at the top here, look at that. They're not lined up anymore. These doors are just, they're kind of getting torqued apart by this flex. If you go to actually try to use the door, it's got kind of a stuckage to it, kind of some friction. The latches are just slightly out of alignment now. So a couple times in my life, actually off-roading these things, you get them up on 3 wheels. This will get even worse to the point where I've seen that you can't actually close the back doors until you kind of level out what your wheels are doing. So in my opinion, every time you come out of a parking lot, you go through one of your dips, the whole van rocks back and forth. The whole time that's happening, the whole body is twisting to kind of accommodate for that motion. And hopefully you've got all your cabinets kind of secured to the walls pretty well, and that body flex is just going to transfer straight to your furniture. There's no way you can build your cabinets, I feel like, rigid enough to overcome that force. So it's most likely to fail as the weakest point in the whole system, which is probably the way the cabinets are fastened to the walls, unless your cabinets can just flex to kind of accommodate for that. If those wall fasteners do start to get strained, they're either going to fail or they'll loosen. So best case scenario, you'll get some squeaking, maybe some rattling. Worst case scenario, if you ever get in an accident, stuff's more likely to come flying off at you. So I think having some flex in your joinery, in your cabinet design, I personally think is really important. And I fully acknowledge a lot of this is sort of speculative, but I do feel like overly heavy and rigid cabinets that don't flex just can't be a good thing for the design of your van. So given that preamble there, what does this test actually look like? So with all our samples here, as well as our 80/20 and our Moxitec, we're essentially going to take these joints and flex them varying distances about 100 times each. This test is assuming that the flexing force is infinite. Basically what I'm trying to say there is, I imagine as the van twists and such, the cabinets have to twist with it. So we don't care how much force is required to flex it, we just care what distance it flexes and how well the joints handle that. To do this, I welded a couple of steel scraps I had together into this L shape. I imagine it is, well, I'm just assuming it's a lot stiffer than all the test samples we have. So we're going to cut some spacers, like this is just a scrap I had lying around. We're going to place that there. Then we'll take our test subjects. We'll essentially put them like that on top of the spacer. We'll clamp it firmly here, and then we'll bounce up and down on this section right here, watching what's happening at the joint. We're going to start out with probably a 1/4 inch, and then we'll probably increase to a 1/2 inch, 3/4, etc. And we'll see at what point things start to fail. My predictions here, I think Moxitec is going to blow this experiment out. I think just those plastic corner connectors are going to have just so much flex that I think Moxitec will really shine in this category. As for the 80/20, it's pretty rigid. I imagine we're not going to just get like catastrophic failures where the joints break, but I think those corner brackets will start to deform to the point where we're not getting an actual spring back to a nice 90°. And as for the wood, I don't actually have any very concrete predictions at this point. Before the first experiment, I would have just assumed that maple is going to destroy pine on this, but I'm actually not sure anymore. As for the actual joints, I'm going to guess pocket joints or pocket screws are going to be the weakest. And formerly, I would have told you that actually mortise and tenon I think will be the strongest. But in the last year or so, I remember watching a video where someone found that half-lap joints are stronger in some application than mortise and tenons, and I thought that was kind of interesting. So it may turn out that the mortise and tenon isn't the strongest, but we'll see what happens. So what actually ended up happening in this test though, I didn't end up needing to cycle the boards at all, it turned out. I'll come back and comment on that in a minute. So now I'll just play the results right after I had finished that test and my thoughts on it just minutes after I had finished it. Okay, so some surprising results right there. No need to cycle any of these joints. I felt like any failure or any shift in the joint happened basically on the first cycle. So I thought cycling these joints through some kind of flex would give us some more interesting results, but that didn't turn out to be true. And after the 1/4 inch spacer, it was pretty clear to me what was happening. So I just moved straight up to the 1 inch spacer so we could kind of get the extreme kind of final result of this test. And I've got some notes to basically summarize what I saw. First off, the Moxitec, as I expected, absolutely shined in this category. These plastic corner brackets, they're a hammer fit, so you cannot pull them apart. Well, you can pull them apart, but it takes a lot of work. Yeah, it just absolutely crushed it. The corner adapter just flexes, no problems at all. So yeah, Moxitec, as expected, did best. Looking at the 80/20 on that first cycle, when we would flex it apart, essentially the little fasteners here in the corner, if we look at one of these, it would essentially just cause, I just couldn't tighten this enough to get enough friction so that this doesn't just shift apart. I think if we did take these and flex them down this way, since it can't just flex apart, we would essentially end up deforming this bracket eventually. There is a little bit more wobble in this than at the start, and you can see that this plane here between these two might slightly be rounded out, so we might have just the tiniest bit of deformation, but kind of a cool like auto-correcting function. I felt like, you know, if you've got a cabinet that is getting flexed, or maybe you didn't quite build it right, so it has to adapt to some kind of surface it's bolted to, seems like the adapters just kind of adjust themselves, so that's pretty neat. So yeah, 80/20 a win there. No catastrophic failures. Maybe you'd get some creaking or some squeaking from that little bit of gap that opened up there, but all in all, pretty impressed by the 15 or the 80/20 in that category. And then finally, that brings us to wood. It's the only one that experienced any sort of catastrophic failures. Basically, on that first cycle, even at a 1/4 inch, all the wood joints, all the glue joints that are end grain to long grain failed. First time I weighted it, it just opened right up. I mean, the glue is basically failed. The screws are still holding it. You know, it is still springing right back to where it should be. But yeah, that was a quick failure. We're at the 1/4 inch here. We'll do this again at the thicker spacers, but that's how that one goes. And then when we went up to the 1 inch spacer, we actually got some catastrophic failures. Clearly the half lap joint just exploded, regardless of pine or maple. The mortise and tenon joint, that whole shoulder area, which is like kind of the outer part of the joint, you can see that being an end grain to long grain part, did crack and fail, but that actual mortise and tenon portion, the innie part of it, it can flex quite a bit. You got some long grain to long grain there, and it didn't seem to fail. Couldn't pull the joint apart, but clearly it had some play, and it was quite negatively affected by the 1 inch spacer there. As for the pocket hole screws, all the glue plane failed. It's end grain to a long grain, so that cracked right away. But you know, screws with their threads, how they pull on the grain, the wood grain and such, still the joint is quite sound. It just is definitely not what it was, nice and stiff when the glue was there to hold it tightly. And then the bridle joint seemed like the most indestructible joint we had. The stiffness isn't what I was looking for in this test, so we'll see how that comes to play in our joint failure test coming up. But unlike all the other joints where I could just easily flex to the ground with my foot, I had to jump up and down on that bridle joint to actually get it to deflect that far. Far and away the strongest joint. Holy shit. I don't know if I can break that. Jesus Christ. There we go. Well, as you can see, this centerpiece has totally just shifted, so I think the bond is broken, but now we just got friction essentially holding it in there. I actually still can't undo it with my hands, but yeah, I mean, it seems like it's definitely compromised, but there we go. That was far and away the stiffest joint. Just the tightness of that joint, since it is kind of constrained between those two outer layers, I couldn't pull it apart. So not quite a catastrophic failure, but obviously if your furniture got distorted to that point where we had that cracking, that joint was in pretty sad shape. Not catastrophic, but it would definitely be, it had a lot more movement than it did when the glue was intact there. So with that, yeah, different results than I expected. And now let's move on to actually destroying some of these things using gravity and some weights. So with that blurb, I agree with everything I said there. But just to add a little detail, I do think that the 80/20, I couldn't tighten the bolts down hard enough to actually get the joint not to just slide apart. As I said, I think if I had tested this, kind of trying to open the joints instead of collapse them, I would have got some different results. But if I had gone down that path, I suddenly would have been doing that for all my species or all my test subjects, and I just didn't want to really undertake that given time constraints. So yeah, that's what I will just say about 80/20 there. And then I think what I was really trying to capture in this test was essentially how well these assemblies can flex to kind of accommodate for that van body twist. And I think thinking back on it now, to have accomplished that, I would have needed to just use larger beams. You know, these things were, you know, maybe a foot by a foot about, you know, 12 inches by 12 inches in that L. I think if I actually built assemblies that were maybe like 3 feet by 3 feet, then the entire actually straight members could have flexed as that joint was getting opened. And I think that may have provided some better insight on how these entire assemblies would flex. But I think for these short little sticks I was using, there just wasn't enough flex in those to really accommodate for the whole structure to be flexing. So yeah, I guess, and then moving that knowledge into the third test, the bridle joint, that thing amazed me. Every other joint, I could just you know, it couldn't hold my body weight without deflecting that 1 inch. The bridle joint though, I had to bounce on it to get it to flex. It was incredibly rigid. This is actually maybe not what I want in a van build, but I think moving forward as I apply this to building furniture, I actually think that this is a really interesting piece of information. So to me, that was kind of a cool, kind of eye-opening moment. And from this whole test, that's kind of what sticks with me. I couldn't believe how strong and stiff this joint was. So onwards to the second experiment presented in the summary video, which is really the third experiment, or what I called the drop test. Let me just quickly explain how I've chosen to present these. Materials and joint type is on the left, and the drop level is across the top. The column the numbers are in is the level at which the test started. So for instance, looking at maple bridle, you'll see like 20, 20, 14, which basically means it survived all 20 drops at the first level, all 20 drops at the second level, and then eventually failed on the 14th drop at the third level. Then I took a new sample and just started clean, like an uncompromised sample starting at the third level, and at that point it failed at the 15th drop there. And if you look at the samples, some of them have 2 different rows, and that just means I ran duplicate measurements just to see if there was some consistency. Of course, wood being a natural material, I expected there to be some variance, and that's pretty clear to see. Let's start talking by pocket holes that were tested in the pine. So there's several different ways to, I guess, load a pocket hole joint. You know, the screws going at that angle, but you could do it like this. You could put them up like this, or even have them face to you like this and then have them broken. So I kind of tested some of these variants. I will say first up though, I didn't think the glue really added anything to the strength in this application. I did think that for maybe normal forces, if you just took that joint, maybe if you were making like a face frame for something, it does help add to the rigidity to have that glue. But the actual failure from dropping things over and over, that glue joint failed right away. You know, in the video I presented collapsing the joint, but as I said, I didn't want to really test every joint splaying it open, but splaying open the pocket hole joints actually did help the strength quite a bit, and it resulted in the most kind of catastrophic like beam failure in these joints, like, you know, a failure of one of the straight members of anything I tested. So that was pretty interesting to see. 13. Wow. $14. There we go. And finally, I tested the pocket holes kind of in this orientation, and that was actually the weakest. It was weaker than either of the other 2 orientations. That just collapsed right away, or broke right away. So that's kind of the summary of the different variants of pocket holes. Moving on to half lap joints, as I said in the summary video, this was the most like explosive joint. It just failed catastrophically. And I think to just dive in why I think that's happening is there is this saying that the glue in a wood joint is stronger than the wood. But what people are saying when they say that is, if you imagine wood, you know, as like that bunch of straws, basically, it's like a bunch of fibers. It's easy, the strength required to split the fibers, like as if you were going to chop wood, is less than the strength of the glue once it's holding fibers together. That said, the amount of strength needed to actually like snap the fibers in half is way higher than the glue joint. So in something like a mortise and tenon, to get it to fail, to actually get the tenon to fail, you've got to snap that tenon, or you've got to collapse and like break the fibers on the side of the mortise. So that's why I think the mortise and tenon is like a far superior joint. And in all my testing, it showed that too. The half lap, just to snap that essentially, or shear that glue plane, was way less strength required. So that's what I would say with the mortise and tenon. Talking about tenon failure, there was actually 1 pine sample and 1 maple sample where I did actually get the tenon to fail. In the pine sample, it happened on either like the first or second drop. 1. Oh boy, this one's going to be terrible. 2. Wow. I think there was just a defect in this tenon, and when I was gluing all of these together, I just wasn't paying attention. And that's something that if I had been making a project I care about, I would have been like, well, there's like a big knot on this tenon or something's wrong with it, and I would have avoided that. But that's just the natural variance of wood. I was just kind of trying to slam all these out, so I wasn't being too careful in like what part of the board I was selecting. And then in the maple tenon failure, that was just, you know, repeated abuse. That sample did pretty well, and it was pretty cool to see that. Not cool to see, it was interesting to see that failure mode for the tendon actually being broken in half. And then finally on the bridle joint, I do think that this joint's kind of weird. It maybe takes the best of both. You know, it's got that sandwiching action. So versus a half lap, when that fails, there's room for these to kind of just separate. This to shear, there's no room for it. I think basically it's like a combination of that clamping force and the ability, the joint can't just move apart once it starts to go. So I think that really helped it. The bridle joint, you know, as I said, incredibly strong for all the wood joints I tested, and I think I'm going to start incorporating it more into some of my furniture projects because of how well it did. And then let me just quickly talk on something in the summary video that I called the edge effect. So I'll just play that clip now that explained it. If you look at these two kind of interlock, and when this broke, it snapped out. And a lot of this is what I call edge effect. There's just not a whole lot of wood between this mortise and then the edge of our test board. So I think I could have biased my results to help wood out more if I had just attached these kind of mid-member like this. I do a little bit of testing to kind of see how much stronger the joints are like this in the longer version of this video. But I would say to feel conclusive about those ideas or those observations I made, I would have to do more testing. So at this point, I just want to point that out, that edge effect really did plague a lot of these, and that is an advantage of the 80/20. It doesn't really struggle with that. So I did end up gluing some joints together to kind of see what would happen if they were glued mid-joint. I ended up gluing these joints in about 1 inch from each end of the board, and turns out that wasn't quite enough to get rid of this like edge effect. I still had some just like fiber splitting as if it was failing on a corner. Broke this little chunk off here, same failure mode. So it would be really interesting if it was truly like mid-run, so we still wouldn't have that kind of corner effect, but that's for a different test. It did help the strength a little bit though. The pine joints seemed to survive a few more drops, especially the half lap actually did help that. And then both my maple samples started to push into like that third level of strength testing, that third drop level, which before this only the bridle joint had made. That said though, the kind of two-sided outcome of this is I should have glued them even further in to actually gain an understanding of what like a midway glued joint would do. But on the flip side, I also learned that there's no way to just like glue them a little bit in and expect significantly greater strength. I think, you know, any structure you're going to make is going to have some joints in the corners. So the take home there is you can't, yeah, anyways, I'm not sure how practical it would be to learn how much stronger a midway joint is. So just food for thought there. A couple thoughts about 80/20 and the drop test. First thing is what delayed this video quite a bit is I was literally trying to film all of this in like the 2 days before I had to leave for Christmas, and I knew I had a lot of work right after Christmas. So the 1010 brackets they sent me and the screws with the little plates, the screws were too short. I could get enough of a bite, so for that second joint flex test, it didn't have issues. But once I actually moved to the drop test, these things were just exploding. So the local stores didn't have the right length screw, so this was just kind of a frustrating process. I bought directly from 8020.net, which to me has always seemed like the authoritative place to buy it, not the knockoff place. So kind of disappointing they sold me the wrong length fasteners, or I don't know, maybe their supply chain has had some issues. So once I finally got those joints, that was kind of a painful setback, something to be aware of if you are buying the 10 series 80/20. So the problem I was having right before Christmas is if you stick these through the bracket, and then you see how much thread is actually coming through there. There's not a whole lot of bite. Man, come on, please focus. There we go. So with these longer screws, we've got what seems like the appropriate amount of thread coming through there. So then these little plate brackets actually have all the threads engaged. So, all right, let's actually get this 80/20 testing done. And then just the only other thing to talk upon that got nixed from the first video is that fastener loosening, how the joints develop all this play. I originally thought, hey, maybe these bolts are backing themselves out. So I ended up drawing these little hatch marks on top of the screws, and that was not the case. It's kind of hard to see in the video. I used a Sharpie on a black bolt head, but in the light I could see it. So it's not the screws actually loosening. It is something about that plate deflecting, or as I said, those little tooth parts of the extrusion kind of getting dented upwards. So just in case you were wondering, it's not the fastener loosening. And I guess the only thing I really want to touch on above here is, if you watch that summary video, my 5th point up front has to do with like the fixation on numbers you can actually measure. And so let me just play that right now. And that brings me to my 5th and last point up front here, and that I hope will kind of set the tone and kind of help you guys understand the lens that I kind of view these strength test videos through. A friend of mine, Eric, recently we were talking about something completely unrelated, but he gave me this great wisdom nugget that I think greatly applies to all these strength test videos and almost plagues them. And that is that I think people really fixate on and kind of inflate the importance of things that are easy to measure. So the way I wanted to apply this is, a while ago, man, it's been over a year now, this guy named Scott Walsh did a joint test video where he said that the half lap joint was way stronger than the mortise and tenon. And I do think that for his test method and for the size of boards he was using, he did get that result. I can't argue with that. But I think this is just one of those applications where reality versus YouTubery, I don't know. I just think that his test, these like slow tests of like putting pressure on a joint, it's just not how things fail. And I think sometimes what I try to consider is like woodworking has been around for like thousands of years now. And if like his results show, I mean, it's like 70% stronger to go to the half lap. I think if over 3,000 years we found that half lap joints were that much stronger than mortise and tenons, they would have kind of become more of a staple joint. While lots of woodworking, the mortise and tenon is like the fundamental joint. And you could say that's from aesthetic choices or et cetera, but mortise and tenons are just regarded as like the strong baseline joint, while half laps are more of an outlier. And I think over thousands of years, much like how evolution works, if the half lap was giving such better results, then I think the half lap would have become the joint to go to. Hey everybody, here from the future, literally editing the video. Just got the screenshot of this fine gentleman here. I think what I failed to do is bring this back on myself, basically. If you watch my video, if you watch his video, you may suddenly think the half lap is going to change your life. If you watch my video, you might think the bridle joint is going to change your life. But the take-home message here is that woodworking's been around a lot longer than YouTube. And I do think for these niche little tests, like his version of a test, my version of a test, we might find some kind of winner. But the overall themes of like what actually works well, that's been figured out for a long time. So I just think stick to mortise and tenons, you'll be fine. Once in a while, from an aesthetic perspective, some of these other joints might do better. And the reality is, for most furniture applications, any of them are strong enough as long as you size things appropriately. So that's just my take home here. I know that my video might come out swinging for the bridle joint, but I'm taking that with a grain of salt. I know it's just another data point, and I just hope my knowledge of how woodworking works continues to grow, and I just thought it was an interesting point that I derived from my video. Yeah, I think that's it. I just had a little bit of a list here in a Word document on what I wanted to talk about, so hopefully you found that interesting. I thought that was some of the more mundane things that I noticed I thought were kind of interesting I wanted to say. So anyways, thanks again for watching. Hopefully you did watch that summary video. Otherwise, I don't think it's going to make a whole lot of sense. So as always, I really appreciate it. This video, I think, was my most expensive video that I just threw away a bunch of material. So, now that I'm at the end here rambling, I haven't posted either video. I am really curious to see how they will do. Yeah, it was pretty pricey, 80/20. I can't believe how expensive it is. I'm really glad that I haven't drank the Kool-Aid on it. And I guess I'm also glad that I have some years of woodworking experience and I actually enjoy it. So yeah, guys, thanks so much for watching, and onwards to the next video. Thank you.